So the last speaker for this session is Jason Ross, and he's going to talk about automatic test case reduction in proof assistance, a case study. So, Jason.
Thank you. So I want to tell you about what I call the coq-bug-minimizer. And to do that, I want to take you back to how I created it, the problem I was trying to solve. And when I first started working in coq, essentially the first project I undertook was formalizing a library of category theory in coq. And I reconstructed what my development process might have looked like one day back then, where I open up an Emacs proof general buffer and I evaluate some code that I had already written, and then I use the tactic split. And split is a tactic that's supposed to work whenever your goal is a conjunction. It should give you two goals for each of the two conjuncts. And you see here that it's giving an error message about an internal part of the proof engine called the refiner, that it can't, it's getting hung up on the difference between type and set. And if you know enough about coq, this is clearly a bug in coq. It's not quite as obvious as when coq says anomaly, please report. But it was still pretty obvious to me that this is a bug in coq. And so I submitted a bug report saying, here's what I'm seeing. But I didn't want to just dump the example that I had, because it's sort of unfriendly to give 3,000 lines of code across 20 dependencies. And so I started trying to make this into a smaller example by generalizing over things that I thought might not be needed. And here you see that on this very simple tactic, it's complaining that type and type are not the same thing. And this is another suspicious behavior. And so 3 minutes after I posted the initial bug report, I posted this follow-up that said that there's something odd going on here. And then I began minimizing the bug in earnest. I tried deleting lines, and you'll see here that that changes the error message. This is not a bug in coq. This is what you're expected to get on this file. And so I needed to back up and undo that change and try deleting other lines instead. And here I'm just trying to delete as many dependencies and as many tokens as possible. And there's a lot of trial and error here, deleting some tokens, see if that changes the error message. If it does, undoing it. If it doesn't, then keep going and try deleting more things. And you see here, I've deleted approximately as many tokens as I can. Unfortunately, there's still almost 2,200 lines of code spread across 13 files. So I didn't want to just submit the development at this stage either. And you can see now sped up massively the next step of the process, which involves taking the dependencies and copy pasting them into this file, which, although it makes it longer, makes the entire bug report less complex, because I wanted to end up with a single standalone file. The other thing you see me doing is replacing some lines with admit or admitted in red. This is coq's way of letting the user say, trust me, this theorem is true. You don't have to check it. And while this is suspicious if you have it in your final development, it's invaluable when you're reducing test cases. It's also pretty useful when you're in the middle of developing, where you can tell coq, I'll come back to this later. Or in this case, oftentimes the error behavior doesn't depend on how exactly you proved some proof further back in the dependency chain. And you can see now that I've gotten a file of 233 lines. It's standalone. And so when I originally did this, it took about an hour to the standalone file. And not too long after that, the coq devs were able to fix this problem. The problem is that it wasn't just one time that I had to do this. I am the most prolific bug reporter in coq. You can see that in green. Of the approximately 9,000 issues ever reported, I've reported over 1,900 of them. This project started because I got tired of manually minimizing test cases to report bugs in coq. The first commit of this project dates to April 2013, and you can see a corresponding jump in my ability to report bugs between 2013 and 2014. The goal of this project is to automate this process, automate the minimization of test cases so that I don't have to spend an hour or more for every individual bug that I want to report. And so you can see here what the automation looks like, sped up to about 8x, or sorry, to exactly 8x real time. On the left, you see the contents of the file. This is the same file that I showed you the manual minimization of. And on the right, you see the output of the minimizer describing what it's doing. And again, it's alternating between inserting dependent files. And when you see the whole bottom move up, that's because it's deleting a bunch of lines in sequence. And it also does the other things that I did, such as replacing proofs with admit. And you can see it took about 3.5 minutes. This is much better than an hour. Even when you don't include the fact that I don't have to be sitting there while it's doing this, I can do other things. There are some minor tricks that I'll talk about later for adequate performance, but at the core, the minimizer is just brute force. It's just trying to remove lines of code. Although I originally developed this tool to help minimize freshly discovered bugs, now that I'm a coq dev, I also see this from the other side when I or someone else makes changes to coq that more other people than me, I don't submit that many pull requests to coq. Sometimes these changes introduce regressions, and these regressions need to be debugged. And I want to give you a little bit of background about what this looks like on the coq infrastructure side, which is that coq does have a test suite, but the coverage of the test suite is woefully inadequate. Much of coq is not covered by the test suite. And so the way that the coq devs deal with this is that we have reverse continuous integration that we test about 75 projects in the ecosystem on every commit of coq, on every pull request of coq. And what this looks like, we now have automation that if your pull request breaks an external development, where breaks here means that it no longer compiles, because coq is a proof assistant that is sort of fundamentally a compiler, then coq-bot will come back and post a comment that says that there were continuous integration failures. And if you want, you can minimize them. You can automatically run the minimizer. It often takes 2 to 4 hours for this message to be posted. Here you can see a scatter plot of how long it takes the CI to run for coq. Green is succeeding pipelines. Red is failing pipelines. Some of the red dots are hidden by green dots. The thing to focus on here is this thick green band, which back when it started in 2018 was around 2 hours, and these days is around 4 hours. And what this means is that you often have to wait about 4 hours to find out whether or not your pull request succeeded or failed, whether or not it broke anything. Once this happens, once coq-bot tells you that the CI has completed, you or anyone really can post a comment saying, coq-bot CI minimize. Please minimize this bug for me. And coq-bot will come back and say, I'm attempting minimization. And a while later, coq-bot will hopefully come back and say, I've completed minimization. And in the body of this comment, it includes the minimized file. So you don't need to go anywhere else to find the development. And ideally, if it's doing its job, the file is standalone. So you don't even need to go download any of the developments. You can just use what it posts in the comments. It's important to ask how long this takes. If it took a week or 2 weeks for it to come back, that wouldn't be very useful. And so here I have a plot of how long the minimizer takes to run, only the succeeding runs, the runs that time out or fail for one reason or another are not here. About 85% of cases where you request minimization, it does in fact succeed. It's actually a little bit higher than that because the statistic includes the invocations of it that came from early on when I was still debugging the integration with coq-bot. About 25% of succeeding runs succeed within 11 minutes. That's around here. Almost half of them succeed within half an hour, almost 75% within 2 hours, 90% of them succeed within 6 hours, over 95% within 12 hours. Currently, if it takes more than a day for the minimizer to minimize, it doesn't actually succeed in reasonable time. Still working on that. The relevant point of comparison here is how long it takes to run individual projects on the CI. How long would you have to spend if you wanted to bypass the minimizer? And although there are some projects that run pretty quickly on the CI, there are projects that take an hour, 2 hours, 3 hours on the CI. And when the pipeline itself takes 4 hours to run, and then if you wanted to run the project on your own machine, you would have to download it and then either download the artifacts or build it yourself. That's another potentially couple of hours. getting to the point from when you submit your pull request to when you're debugging is going to take a while. It's going to interrupt your workflow. And so adding another couple hours or even a day in the middle of that isn't really going to impact your workflow too much, especially given that you don't have to load up any state to ask the minimizer, please minimize this. You just leave a comment on GitHub. An important proxy for how useful the minimization is how much we minimize. Here you can see the reduction factor in lines of code as well as in amount of time. And this is the percent of runs of the minimizer of the successful ones that achieve that much reduction. Over 60% achieve an order of magnitude reduction in the number of lines of code. 30% achieve a reduction of 100x or more. And in terms of time, 50% achieve a reduction of nearly 1,000x reduction in time. This is time it took the CI to fail versus how long it takes to compile the minimized example. And over 90% achieve a reduction rate of at least 200x. As far as absolute lines of code and amount of time go, oops, I should only have the percentages on one side, but it's fine. Yeah, as far as the absolute numbers go, almost 80% of the test cases take at most a second to run. This is pretty quick. And almost 95% run within 10 seconds. Again, the ones where it takes more than 10 seconds for the test case to run once are probably going to fall into the cases where the minimizer failed to minimize in a reasonable amount of time. And that's that 15% or so of cases. And almost 80% of the test cases have at most 100 lines of code. So these are reasonably minimal examples. I want to talk now about what exactly we want the minimizer to do, what the specification is. The input is that we want to point the minimizer at a development displaying a potential problem with coq. And I say potential here because it's not always clear what is a bug in coq and what is a bug in your understanding of coq. For example, if you say, coq, please replace 1 + 1 with 2, and there's a 1 + 1 in your goal, and coq says, I can't find 1 + 1, maybe you think, well, obviously that's a bug. But if your goal was something like 0 equals sine of pi times 1 + 1, it might be the case that your goal was talking about real number addition, and the tactic got interpreted as natural number addition. And really what coq is saying is, I can't find any natural number addition in your goal that involves real number addition. Maybe that's a bug in the error message. Maybe you think coq should display better error messages. But the point here is that it's not always clear what is at fault for the behavior. And so the output isn't supposed to say whether it's a bug in coq or a bug in your understanding. It's just supposed to be a shorter, smaller, faster file, single file, ideally, displaying the same behavior. And the things we want here are that the file should be standalone. It should be as short as fast as possible, as fast as possible. The process should be fully automated. There should be no interaction beyond pointing it at the issue initially. You shouldn't have to interrupt your whatever else you're doing in that couple of hours multiple times. And finally, ideally, it should be interruptible and resumable if you do want to have more manual control over it. The user should be able to do a manual pass over the file at any point and then resume the automatic minimization. I want to note that this final bullet point isn't hard to do. It sort of falls out naturally, but it is quite useful to have implemented as part of the workflow. There's some subtlety in terms of what the same behavior means. For example, if the minimizer decided in the test case that I showed you earlier to take the entire file and replace it with print, the refiner received a term of type, and it was expecting something of type set, or whatever the exact error message was. That's not a valid minimization. That doesn't explain anything or help us learn anything about what's actually going on. And the heuristic that I use to get around this is that the final bit of code, technically anything from the last theorem statement that involves the error message up to that point of error, is not allowed to be changed. It has to keep the same tactic, the same final bit of proof script, generating roughly the same error message. And there's still some subtleties here. For example, we don't want the line numbers to have to be the same. We don't want the universe numbering to have to be the same. There's some subtlety there that you can read about in the paper or ask me about. In the CI case, in the regression case, we can be a little bit more lax because we also have a version of coq that's supposed to succeed. This is actually a regression. The behavior should be different on the master version of coq and on the version of coq that was modified. And so we require of the minimized file that whatever behavior you're seeing on the minimized example, it should show that behavior on the modified version of coq, and it should succeed on the master version of coq. And this would let us be a little bit more lax with the same bit of code condition. I haven't implemented it yet, but on my to-do list is allowing modification of that final proof script and allowing simplification of it. What needs to be automated to make this all work? We need workflow automation. That is posting the initial comment from coq-bot that the CI failed, responding to the user's comment, replying as a comment, spinning up the GitHub Actions server to run the minimization, having it download the code, all of these bits of glue around the edges. As far as the minimizer itself is concerned, we need to remove code to shorten the example. We need to do adjustments largely to minimize compile time. This is things like replacing proof scripts with admit with trust me, it's true. And inlining and linearization of dependencies to reduce complexity of the final example to make it easier to compile and play with. And the way that we do that, the three main techniques are, or sorry, not three main techniques. The three main bullet points here are that we're interfacing with coq externally. We just run coq on every change we try. Turns out that this is fast enough for 85% of cases. We basically use brute force for removing lines of code. There's a fancier technique called delta debugging that we sort of implement. There's a lot of overlap between delta debugging and what we do, but I like calling it brute force. And there are some tricks for how to inline dependencies. There are three main techniques that we use to achieve adequate performance. We inline files one by one instead of all at a time. This makes the overhead of running coq after every change manageable. We remove proof scripts as early as possible, replacing them with admit, because coq spends most of its time generating proofs, checking proof scripts. And what this means is that if we can eliminate them, eliminate the unnecessary proofs as early as possible, we can drastically reduce the runtime. And finally, we manage to achieve essentially a linear path to remove code. We don't have to consider removing multiple lines far apart simultaneously. And I will talk about how we achieve these things. In the realm of removing lines of code, it's again essential to have these trust me it's true primitives, these admit, admitted, to remove the overhead of running proof scripts that you don't need to be running. It's also important that we're not removing things line by line, we're removing them in blocks. If you remove the middle line of a theorem statement, you shouldn't expect the result to be valid, let alone true. We also don't want to remove the middle of a proof in most cases. We want to remove the proof all at once. And we don't want to remove a theorem without removing the proof. Coq won't be able to make sense of the proof if you don't tell it what you're proving. Coq has minimal coupling. It has a lack of forward references, which is what allows it to have minimal coupling by and large. And let me explain what I mean by this. In Ogda, for example, if you want to prove something about natural numbers involving evenness and oddness, you might write some code like this. And if you have some code later displaying questionable behavior that doesn't reference evenness and oddness, you would want to remove this block of code that says even and odd. The problem is that even if you break it up into separate statements, it's not valid to just remove some of the statements. If you remove just odd, you get an error message saying that odd was declared but not accompanied by a definition. Similarly for even, if you remove the declaration of odd, you're told it's not in scope. And if you remove the declaration of even, you're told that it's missing a type signature. You need to remove them all at once in order to be error-free on this part of code. And even worse than that, you could have had other statements between those four things. They didn't have to be contiguously aligned in code. And so it's very hard to figure out where you want to be removing things. In coq, by contrast, you have this single statement ended by a period with a mutual inductive data type. And so This is a pattern in coq that in almost all cases, when you have coupling between different definitions, they show up largely as single statements. You can't insert other definitions between even and odd. And because of this, we can remove these blocks of code, these statements, one by one in a pass from the bottom to the top. And it is almost never the case that we would fail to remove something that we could have removed if we removed it at the same time as something else. And this drastically improves the, drastically reduces the number of things we have to try. As far as inlining goes, there are two main considerations. The first one is that inlining can change the names of definitions. If you just copy paste the contents of a file, the way you refer to things in that can change. And roughly our trick for this is wrapping things in modules. This doesn't always work perfectly. There are a large number of very subtle issues around this. There are, I think, 3 or 4 or 5 different varieties of wrapping things in modules that we try. And as with so many things in the minimizer, the answer that we use is brute force. We just try all the different ways that we know of to inline. We see if any of them work. The other, perhaps the most important consideration in inlining is linearization. That is, when you have a file C that depends on A and B, which don't depend on each other, do you do A and then B and then C? Or do you do B and then A and then C? Again, we use brute force. We try them both. There's actually a couple more questions here about where exactly in the file you insert the dependency. And so we try more than 2 things. In 86% of the files that the minimizer succeeds on, they are fully standalone. And so this brute force try all the things works for 86% of the files, which is pretty decent. I expect that some of you in the audience might be proof assistant developers, possibly not of coq. And so I want to leave you with some tips of how to make your proof assistant amenable to minimization. And this might be of interest even if you're not a proof assistant developer. First, make it possible to have a single file with the same semantics as code in multiple files. This is not essential, but it is very useful for minimizing the complexity of the minimal test cases. The primitives for trust me, it's true are absolutely essential in reducing the amount of time it takes both for the final example to run and for the minimization itself. Having a lack of forward references, a lack of coupling is nice. If the proof assistant language has coupling, you need to do more work to try to figure out what subsets to remove all at once. And finally, don't forget the last mile of integration with the CI, with continuous integration. When we integrated the minimizer with coq-bot, the number of apparent uses and users drastically increased. And I think I also found that this increased usage led to a quicker improvement of the minimizer itself. Future work is first more automation. We currently only integrate with coq-bot well for the regression case when there's some pull request to coq. The bug reporter workflow does have a little bit of integration with coq-bot. But the main problem here is that it's not always clear when you're reporting a bug, what exactly your dependencies are, what versions of them you have, what version of coq you're using, how the ecosystem is set up, what your build commands are, what other files you're depending on. Whereas for the CI case, we already have a reproducible example that failed. We have the failed CI run, so we can just mimic that exactly to reproduce the behavior. I think that automating this workflow more would be a great boon. We could also do better inlining in those 14% of cases where we don't produce a standalone example. It would be useful to make standalone test cases in more examples to work around more edge cases. The most recent one that I worked around is that coq lets you have a file named prop, but it does not let you have a module named prop. More minimization is also great. There are cases where coq does have coupling. That's the main place that we can potentially get more minimization, although there's also the minimize the final proof script. In those cases, I have some ideas for how to do more minimization. For example, removing a constructor from an inductive type and all uses of it at once, or removing a field from a record and all uses of that field. But these are significantly more complicated. And as I said before, about 80% of cases, we manage to be under 100 lines of code. And so this isn't absolutely essential. And finally, I would love to see similar things work for other proof assistants. I don't have any concrete plans to port this tool, but I'm more than happy to act as an advisor or chat about it. Thank you.
Questions?
There's something that you alluded to at one point when you showed your manual minimization process. So there's something that also I also often experience, that I have to change the goal that I'm trying to prove because it's a very complicated goal, and quite often there's only a few features that are necessary to exhibit the bug, the behavior. And I was under the impression that your tool is not working in this direction. Did I understand correctly?
That's correct.
Yes. Can you expand a little bit on your opinion on that?
So the tool does not do this yet. I do have some ideas for things like I could try to automate the process of see what you could generalize over, or like start by looking at the goal right before the error line, try copy pasting that, see if that still reproduces the error, try systematically generalizing over the goal and figuring out what bits you can generalize over. So I do have some ideas for automating this. In 80% of the cases where it succeeds, and which means, what is this, something like, gosh, I can't do mental math in my head anymore. What's 80% of 85%? 60-something percent. In that proportion of cases, it successfully manages a small example. So it's not completely essential, though it would be useful to do. And there's also the resumption that once you get that message where here's the smaller example, you can go and try to futz with the goal yourself and make it a little bit smaller, and then send this back to the minimizer and say, minimizer, please start minimizing again from this altered goal. And this often, I found, gets another order of magnitude or two reduction. And when you do this, you don't have to spend a lot of time minimizing the dependencies.
That's a good idea.
Yes.
So the specification of what a good minimization is that you presented, have you encountered errors where the specification would not work? So just a trivial example, I expect some rule to be in scope, but I get an error. I did not find this rule. I did not find this name, but the name should be in scope. Just as a trivial constructed example. And if I then remove the rule, you will still get the error message. The rule is not in scope, but this time it's not a bug.
Right, and so, yeah, so that's a deficiency in the bug case example. In the regression case, because it's supposed to succeed on master, we don't hit this, right? Because removing the rule would make it have the error message in both cases. I have almost never found this to be the case. Usually the bugs are a lot more subtle. If you have a bug that is like this, you could do something like find it in scope in some other way, like maybe if one thing can find it and another thing can't. And then you could write your tactic and be like, error with one message if the first thing can't find it in scope, otherwise error with second message if the second thing can't find it in scope, and now the error message will change if it removes that line. So there have been some cases where I've sort of hacked the minimizer by saying, here's this complicated script to detect exactly the behavior I'm looking for. In that case, print error behavior found.
So in most cases, it's not a problem, and there it is, you can work around.
By and large, yes.
Yeah, nice.
Yes?
Thanks.
Yeah, go ahead.
Thanks. So this is very cool. I would obviously love to have that for all four. So my question is, how much information do you need to encode in the minimizer about the syntax of the files?
So there's essentially no information in the minimizer for the syntax of coq. Coq has this neat thing where you can give it a command line argument that says, please print the timing of every single statement, and it comes with byte ranges. And so we just tell coq, please print the timing of all the statements, and that's how we break it up into byte ranges. And then we pass another option that we parse the output of that says, please tell me when you're in the middle of a proof and when you're outside of the proof, and that's how we chunk it into bits that are like, here's where this block of code is. So we do need some way of parsing the file. We managed to get by without much information about coq. And once you have that, the actual minimization process is basically just over lists of strings. It says, try removing this string, try removing that string. There are some regular expressions that are like, this is what a proof block looks like, try replacing it with admit. But you don't need that much information.
So this obviously is also potentially interesting for languages that aren't proof systems.
Mm-hmm.
Do you know if, and they obviously also have way larger communities. Do they do things like that? Do you know?
So I don't know if it's automatically integrated with the CI for anything like that, but Delta debugging is prior work. There is a tool that sort of just removes well-parenthesized blocks, and it can also do it across multiple files. It doesn't do the inlining. It doesn't have anything for replacing proof scripts with admit, which is one of the most essential transformations that we do for minimizing compile time and minimizing minimization time. But it does, that tool also sort of works externally. All you need to give it is how do you parenthesize your code into well-delimited blocks.
Okay. Yes.
So coq has some support for paralyzing compilation, which precisely involves farming out proof blocks to workers. So do you think you could leverage that somehow to get the part of the work done for you?
I think that would be cool to leverage. I think even before that we want some sort of caching, either with coq-LSP or by using coq-top's backtracking mechanism. I think another place to do this is we could try parallelizing by trying multiple changes at the same time. I don't know if this would give better or worse results than parallelizing the individual blocks, but I have found that it does seem to be more or less bimodal in that most developments take not that long to compile, a couple hours, whereas other developments, if you actually want them to fully minimize, you'll have to leave it running for like a week or more or something. I did once leave it running for, I think, a week or two. This was back before I was inlining files one by one and did them all at once. But I think that improvements around optimizing the final proof script and caching, I think we want to do those before we try parallelizing.
Last
Well,
question.
it's not especially paralyzing, but just
You mean
there's already code that splits out blocks that can be done separately.
Yeah.
So
Oh,
you
right.
could,
I
you
see.
could just tell the system, well, just put them.
I don't think there's any, and I don't think there's currently any support for prioritizing the ordering of that, though. And I think we achieved something that's almost like that by replacing opaque proofs with admit very early on. So any proof tasks that are not actually essential for the final code just get replaced with admit pretty early.
Yes, but you could speed up even your initial run by saying, oh well, just do this.
Yeah, that's true, but I think this is not where the bottlenecks currently are. But yes.
So last question.
So how feasible would you say would it be to integrate deeper with coq itself?
To integrate.
Deeper with coq itself, so to reuse the AST, not having to actually go through the whole pipeline for every change, and in turn also maybe having the option of just when you have something that fails, turn on the minimizer on the coq that you already have, and then you can minimize that, and then have a better bug before you do it.
I see, doing it locally. Yeah, I think especially if this, I think the best path for this that I've seen so far is Emilio has a tool called coq-LSP that lets you, I think the main neat thing that it supports is caching. And so you could have some mode. Yeah, I guess there's sort of two things that you want here. One of them is you want something that just like takes your system as it is and like uploads the state without necessarily doing minimization, and this should ideally be relatively quick. And then you might also want something that does some of the minimization on your client machine before reporting the bug. The problem with this, though, is that it does take often half an hour or a couple hours, and you don't necessarily want to wait a couple hours of your own compute time while it's doing stuff before reporting the bug.
Yeah, I mean, the hope would be that it's faster geometry computation, right?
Yeah, right. If you have caching, it could potentially be much faster. I could see that being worth it to do before reporting the bug.
So this is really cool. When are you going to port that to PBS? But I'm curious.
When I have some more people to help me.
I'm curious. What are you doing that you are finding so many bugs in coq?
I think it's just that I'm taking the error messages that I get more seriously. I'm like, every time I get an error message, I don't assume that it's my fault or that it's a thing to just work around. I'm like, oh, I didn't expect to get an error message here. I don't understand it. Let me sink 2 hours of my time into understanding it. And I did this to the point where I understood coq and developed the minimizer.
Yeah, this is good. Okay, thank you.